All right, so welcome back. I hope everybody had some time to unwind or catch up on their work over the Thanksgiving break. So we are on the final stretch of our course and our third module. Since I skipped 2 lectures because I was traveling to different conferences, this module will extend into the last lecture that we also have, right? So typically I reserve the last lecture as just a full recap, but I think this time we'll have to do a bit of both, wrap up the module and the lecture. So we'll continue, in this module so far, we began with this motivation for the use of data-driven algorithms for autonomous CPS. So it's a very high-level sort of task, and then we made it more specific and tangible by focusing on a certain class of data-driven models which don't require any physical domain, nor do we care about correctness and things like that so far. And so we just want to map some raw data to some model output. And to do so, we stuck with the example of convolution neural networks, which build upon fully connected neural networks to begin with. And we had a little detour, as always, to go deep into understanding the framework of the modeling and the principle of modeling. But now we come back to the domain and look at how what we have learned applies to self-driving cars. And in particular, I want to focus on deep learning for autonomous driving. Once again, deep learning for autonomous driving is like a big topic on its own. And in the final lecture, I will give you a preview of all different sort of applications of what you have learned, how most of what we see in self-driving car prototypes are using, these AlexNet and other VGG16-like networks to do a lot of the scene understanding part. But to, again, keep us focused on the task of mapping what we have learned onto the task of autonomous driving, I will begin with a specific application on lane detection. Okay, so as always, shout out to everybody who's prepared a lot of slides, and I'm just reusing most of them. So they have done a good job of preparing a lot of slides for me. It saves me a lot of time. Okay, so far, we've done what you can see in this picture, more or less, where we have seen that architectures like AlexNet, which are trained on the ImageNet database and similar databases, they can do this task where we have input image and we have a series of conv pool ReLUs, and there may be some other type of layers that we haven't yet discussed. But the essence of it is that you have to produce the output class label or the most likely label going through softmax and things like that. And I have been showing you this video several times where if you think about it, every vehicle that you detect is going through the same pipeline as the previous picture. What is not clear is how are you searching for where the vehicle is in the scene. And that's slightly more complicated task, and I think someone had actually brought up this question earlier. So maybe you'll find your answer by the end of the lecture today. But to get us started with the applications of deep neural networks for self-driving, I want to look at the task of lane detection. It's the 101 of autonomous driving. You have to be able to detect what lane you are driving in. Humans don't even think about it. We can see and very easily figure out what is our lane if there are lane markings or if there is no snow on the road, subject to all that fine print. But for autonomous lane keep assist and other technologies, even if the car is not controlling itself on the lane, many cars have lane departure warning. They are also detecting where the lane are, especially what is the lane of the car, the lane in which the car is driving, and the car is sometimes referred to as an ego vehicle, so that we refer to this as detecting the ego lanes. And this is not always right. So here is a self-driving car prototype or level 2, level 3 prototype from Tesla Autopilot. I don't have anything against Tesla, but this video conveys my point from YouTube. So let's watch this video. I wonder if we have audio, but even without audio, it should be interesting. Okay, so there's no audio, but you see this car is driving, and all of a sudden the left barrier is there's no lane, and the car doesn't figure it out, and this person has to correct itself. And actually, I'm kind of glad there is no audio because this person is just like cussing all over the place, right? So So even these cars are being driven. They are in commercial production. They are getting tested on public roads, and they do face these sort of problems. Actually, I want to play this video again just to convey a different point altogether. This time in favor of Tesla. So if you watch this video again, so here's your first clue, right? It says merge, and the person still relies on autopilot to figure it out. And then you drove forward. There's another sign which says 2 lanes ahead instead of 3. There's another sign which says merge again, right? And this person is just ignoring all those actual traffic signs and over trusting this ability of lane keep assist, right? So the meta point I want to convey is that these systems still require driver oversight, right? And so you should pay attention and treat them as you treat regular cruise control, where you have to take over at any time. And we've sort of seen this example even before when the car was entering a tunnel. So here is the same sort of view, and what we have overlaid on top of this is the actual image from the front camera of the car. And you can already see that the way the front camera processes images is different because it's much darker. It's also because it wants to reject all the direct sunlight. That's why the overall image is darker. But if you notice on this image, the sunlight reflecting on the top of the barrier can be interpreted as a lane marking. And so that can explain why the car still thinks that there's 2 lane markings on both sides. Right, so the point being that we have come a long way in doing lane keep assist and lane detection, but there can still be mistakes. And the point of the lecture today is how can we use the machinery that we have learned to solve and attack this problem. But in order to explain you and you have to experience the pain of not using deep learning to appreciate why it is better. And we have made this point at a high level before. I have said many a times that the human doesn't have to design the features themselves, and the filters of the conv layer are essentially learnable. So just based on data and labels, you can learn features to do classification. I actually want to first show you the entire pipeline of how you would do lane detection without using any neural networks or any even data-driven algorithm for that matter, just so that you experience all these steps, and then you will have a much more appreciation for why deep learning is a preferred method. Or maybe if you don't have an appreciation, you at least have a comparison of whether or not you think it's useful at all. So here is a roughly dozen steps that you would want to take, and I'll very quickly go over this. This is not a computer vision lecture, but I'll go over most of these steps with many, many examples to quickly give you intuition for how you would accomplish this task without using any convolution neural networks, right? So the task roughly is you have the input image on the left, and you want to build an algorithm, not a network, to generate something which resembles the output on the right, where the output is that you have figured out where all the lane markings are. So it's actually even a higher task than what we started before. At the very least, you have to figure out where the ego lanes are, so the left and right boundaries of where you are driving. So to do so, the very first thing which comes to mind is you don't actually want to use RGB color space. So red, green, and blue channels is typically what camera outputs by default, but you can transform that information into a different color space. So once again, I'll be fairly quick about what this is and why it matters. So you can think of the left image as a typical state space of the camera output in the RGB channel, right? So every pixel is some point in this RGB 3D space. Another color space is what is called HSV, or hue, saturation, and value space. Hue is really telling you what is the dominant wavelength or color, again, of any individual pixel in the image. So you can visualize this cylinder on the right, where colors are sort of on the periphery of, or the radial axis of the cylinder. Saturation tells you how intense that particular color wavelength is. So saturation is, akin for intensity. And then value tells you the darkness or the brightness of that pixel. Right? So you can go from RGB to HSV. In fact, another color space is also called, very similar to HSV, is called HSL, where hue and saturation is still the same, but the L channel, instead of giving you just the brightness of the pixel, it gives you how much white content is present in the pixel, right? So it's slightly different. So why do we care about these color spaces? Well, we can take our image on the very left and we can convert them into the equivalent HSV and HSL maps. So on the very right, most image is one which appeals to us, because you can see in the hue, saturation, and light color space of the original RGB, the lanes are very predominant. They like prop out, in other words. And so you would manually want to convert everything into HSL before you do all of the rest of the image processing to detect the lines. So how does the lane detection already work to begin with? So let's say we change everything to HSV or HSL. Then what you would want to do is, lanes in the United States are either yellow or white. And so you want to isolate all the pixels which are either yellow or white from your image. So the center mask is telling you which pixels in your original image were yellow. And we don't have any yellow lanes in our original image, but the traffic signs in the horizon are yellow and they are getting picked up. And then the rightmost image is the same thing, which is just a white filter, right? So it's telling you everything which was white in the original image. And so we pick up lanes, we pick up the rear of the sedan or car in the adjacent lane and so forth. Okay, so we are still processing our input space. And you can actually merge both of these into a single sort of image, or compose it with the layers of the white and the yellow on the same image, and you get the output on the right-hand side. Then another sort of trick you do is you apply Gaussian blur. So again, I won't go into details of the math behind Gaussian blur. The effect is, on the left-hand side, you have your combined white and yellow space image, which was derived from the HSL view. And you can see there's noise, right? There's all these sort of dot pixels or line segments in the air. Gaussian filters, roughly speaking, is a way to get rid of this noise. And so output is shown on the right with slightly less noise. You apply another filter where you are now going from the yellow and white pixel space in HSL to grayscale images, right? So we have seen before, grayscale images are images where pixel values are between -1 and 1, and the gray is 0. So just easier to work with numerically, and it also actually gets rid of some of the noise as well. So after so many steps, you are finally at the image on the right-hand side, which is grayscale image of the filtered white and yellow channels of the HSL of your RGB. Okay, that's the pipeline so far. Then you actually do your first sort of real algorithm, which is called canny edge detection. It's one of the most popular edge detection algorithms. The way edge detection works is simply, it looks at all the pixels of your image, and it's going to keep track of gradient of pixels. What do we mean by that? We want to keep track of which pixels are the ones where the value of the pixel abruptly changes by a large magnitude. So we are scanning all the pixels in our image to find those pixels where the difference between left and right is 1 or -1. Guys, all the background is all black and the white is the +1 value, let's say. And so that's the output which is shown on the right-hand side. And that's akin to saying that you have detected edges in your image. And so once you have the edge detected image on the right, it's still not clear, where the lanes are. We can tell as a human, but for a computer, we have to get rid of all these other points which are also getting detected with edges. So another trick you do is you select a region of interest in your image, and you only preserve whatever pixels are within the region of interest, and you neglect everything else. So I'll show you how this works in RGB space. So here's your original image, and on the right is my region of interest mask. So essentially, I'm manually selecting some value based on where the camera was on the car at the time, and I'm going to ignore everything which is outside of this region of interest. So this can help you to go from the left-hand edge detection image to the right-hand side. Yeah?
So why could we do the region of interest at the very beginning?
Good question. In this case, you could have done, but in general, for lane detection, you actually don't want to use any region of interest. Also, it depends on whether your lanes are curved or not. That's another reason. But for this example, the order doesn't matter. So another property is the region of interest would only work if your lanes are always within this region of interest, or the camera is always in the same place from maybe one data set to the other and things like that. One more trick that you want to do is you want to take your original image, and let's say you have a region of interest. The problem is for a flat image, it's not big of a problem, but your lanes are not parallel in the original field of view, and so it's easy to fit straight lines on data is the intuition behind it. So what you can do is you have a region of interest or maybe even an initial guess of where the lanes are, and you can transform this red polygon on the left-hand side such that the left and right boundaries of this polygon are parallel. And so when you do this perspective transformation, you are actually distorting your original image. And many times in the world of self-driving, the right-hand side image is misinterpreted or called like a bird's eye view of what the scene looks like, because it actually looks like someone is observing where the lanes are on the top of the car. But it is just a perspective transform. So why did you do this? You do this because you again have either the output of the canny edge detection or the region of interest. You can do this perspective transform, and what you will get is something which is similar to what is shown on the left-hand side. And then you can do a simple search or a histogram. The histogram on the right is plotting the values of the pixels of where. So for each column of the original image from 0 to 1200, we are plotting the intensity of the column, the white channel or the white bitmap for that column. And we do this for all 1200 columns, and you will get a histogram which will tell you where in your original image on the x-axis. Why do we care about the x-axis? Because this is a perspective transformed image. So everything is like parallel looking forward relative to the x-axis of the image. And so this is going to tell you where is the lane information, or which pixels have the two lane boundaries. So the histogram is already looking like the width of a lane for you. And so the final thing you do, again, I'm going over this in very high level detail. You take this information of where you suspect the lane markings are based on the histogram, and then you can fit a sliding window or a box beginning from the bottom of your image, add those x values, and just keep sliding the box wherever you find this white band in the original image. Okay? I don't know if I did a good job of explaining it, but I hope the image here makes it clear on what this sliding is doing. Finally, once you have all these sliding windows, which may look like something on the left-hand side here, you can fit a smooth line through them. And this is something called a hue transformation as well. And once you have your left smooth line and the right smooth line, you can project it back using this inverse perspective transformation onto the original image. And that will give you an idea of where the lanes are in your original image. Okay, so let's look at how well this could work. So on a relatively straight lines, it's doing a good job. There is some jitter, but now you can see we're approaching a very slight left turn. And while we are doing a good job of figuring where the lanes are in the near vicinity of the vehicle, you can see on occasion we just completely lose track. But overall, I would say it's not that bad. And you can actually see the output of all of the individual tasks that we did at the the top of this video. So there are some limitations, of course, of this work, where the perspective transformation is very specific to the type of camera, its focal length, and its setting and specifications. All these thresholds you are using, the region of interest, all this sliding mechanism, it is very sort of individually hand-tuned or hand-picked. There's no way of learning it automatically. And also this algorithm takes a lot of computation, right? You're doing so many steps. So in real time, you have to process like at least 60 to 100 images per second, and we cannot really do that with such computer vision architecture. But most importantly, I want to emphasize that all of these steps, how well they work, and you can make a case for improving the computation time and the accuracy. It's still very manual, and this is what I mean by saying that traditionally all these computer vision tasks were done, stitching up these manual pieces together. It still solves the problem. We saw the output. It's decent. It's not very accurate, but it's not that bad either. And another limitation is that there's no way of saying how well you will perform on other data sets. This is very specific. Your choices of these parameters depend upon lighting conditions and all these things. Right? So maybe one choice of the parameter would work for just daylight, and it wouldn't work at all when there's fog or at night when there's glare. Right? So in fact, even on this very simple, supposedly right turn, you actually have a true lane, but then you have this tarmac. Let me highlight it here. So the true white lane is here, but then this black thing is just some tarmac lane, artificial lane on the line. And then this can be interpreted as the shadow can be interpreted as a straight line. The top of this barrier can be interpreted as a line as well. So it really depends upon your region of interest and all of these choices that you have to make to get it right. In even a straightforward scenario, there's no other vehicles. Nothing is occluded. And so if you are struggling on even this scenario, this is reality, right? So there's shake on the camera. All images are not super high definition. They get blurred, so you will lose this information. In fact, this is even difficult for a human to figure out what's going to happen, right? So you can try doing some perspective transforms, but they don't work that well on that previous image. And I don't even know what's going on here, but a self-driving car has to deal with these situations as well. Yeah, this is interesting too. For some reason, this line just curves around. And if you have only looked at this sliding window to detect straight lines, you will miss this curve. Okay, so there are problems. It's doable, but there are problems. And when it is doable, it takes a lot of expertise. And what CNNs, on the other hand, is let the data be the expert. Okay, give me good data which is labeled and has good lane markings and everything, and let the network figure out what the best features are. So in some sense, the layers of the network are doing their own internal transformations and filtering and edge detection, unknown to us. Or we can probe and visualize the layers, of course, but we cannot control what layer does what. So that was just a brief detour to convince you the pains of solving the simplest problem or the straightforward problem with self-driving cars. And we are struggling using domain expertise. So now let's jump ship and look at where deep learning can help us. And so this has been an area of a lot of attention that's always improving. I'm going to describe something called lane net. Not surprising. Anytime someone builds a network, you look at what it does and then just append net after that. So here's one idea, right? So think about what would the labels of an image that you want to detect lanes in would look like. And here's one idea, that for every RGB image, my label or output that I want to generate would be a mask, where the only non-black pixels in the mask are my drivable lane. In other words, I want to train a network that takes a RGB image and learns this mask, which is similar to saying you have learned where the lane is, and then you can even impose this mask back on your RGB domain, right? So let me show you the output first, and then we'll see how to do that. So I think I've showed you this before as well, but now you know what I mean. This is the output of a network which has learned to project this green mask onto every frame of this video, right? So instead of just predicting an output which is vehicle or not, or this is not a classification problem anymore. We are not saying cross or zero. We are actually generating which pixels in my image belong to the class lane. Okay, so it's very interesting, and for the remainder of this lecture, I want to show some of the ideas behind this, and you can see it performs reasonably well. This is not the only solution, by the way. Another thing you may want to do, and this kind of overlaps with this video that I've shown you of vehicle detection, you can think about what would be the ground truth, or what's the data set that we can use to learn these bounding boxes around objects of interest, or learn where the lanes are. So here's one idea. You have your, let's say, the plane image you have on your on the left-hand side, and then someone manually has to go in and label where the vehicles are. So the yellow boxes are where the vehicles are, then the traffic light and the pedestrian. So this is the manual labeling task. And you can do that for lanes as well. So in this picture, someone has labeled where the vehicle is, and you can draw, this polynomial line, or this line segment on top of the lane markings. And all this metadata that you are adding on top of the image is getting stored as the ground truth labels, right? So in this picture, we combine everything together. We have vehicles, we have a label for left lane, a label for right lane, traffic lights, and pedestrians. And you can see all these labels are here with their corresponding colors. And so you have to painfully, draw these ground truths onto a real image. And then you can train some network to predict these ground truths for an unseen image or a test data. Right, so in case of lanes, one idea was this segmentation mask that, again, you have to paint over the original image to generate the ground truth for. Another idea is if you are just fitting polynomials, you can just store the coefficients of these polynomials. Right, so in the previous image, the left lane has 3 coefficients and the right lane has 3 coefficients, and we are just learning for every image what were the coefficients. And so if you have a CNN, you can modify it to, instead of predicting the class of the object, it will predict the values of these coefficients, and that will be the lane prediction. So these are 2 different ideas. One is, let me draw line markings as polynomials and represent them as polynomials. The other is, let me just use a mask on my image, but they're very related. So questions so far on, we haven't really looked at how to solve this, but is the setting clear, what we want to achieve? We want to figure out what sort of networks to train to solve this problem of either the bounding box or the polynomial or the segmentation mask. Okay. So far, what you have done and what you are also doing in your homework with the crosses and the circles is similar to this problem of what AlexNet did on ImageNet. Right? We have some data, you have your convolution neural network, you have fully connected layers, and then you predict your class scores. With a softmax, you can convert them into probabilities. But what the kind of lane detection tasks that we want to achieve are slightly different nature. They are not just classification tasks of whether an object is present in this image or not. So to begin with, we have semantic segmentation, where the idea is that I want to assign every pixel of my image its own class. Okay, so it is still related to classification, but the output is not just a single label. You are producing a label for every pixel of your image. And the output would look something like this. A slightly more different task is, yes, I do care what object is present in my image. So here's a cat, but we care about vehicles. However, I also care about, can you draw a bounding box around where that object is present in the label? And so we've seen that to be able to do something like this, you need the data where someone has labeled not just which object was present, but what's the bounding box around that as well. So this is what is called classification plus localization, means where this bounding box is. Slightly more complicated. So here you actually assume that there's going to be a single object, right? So I know there's one object I'm looking for. I need to tell you which object it is and where is it located. A slightly difficult variation of this is generic object detection, where I don't know how many objects exist in my image, but I need to sort of find and localize all of them. And then the most complicated task is what is called instance segmentation, where first of all, I care that if there are multiple objects present of the same class, I have to differentiate between them. So I care about that this red one is dog 1 and the green is dog 2. And instead of bounding boxes, I actually want to paint the pixels of where that object is, right? So these are progressively difficult tasks. And so we'll understand a few of them today and then map it to the lane detection problem. Okay, so we'll begin with this task of semantic segmentation, where the idea is we want to, like I said, instead of one label, which is cross or zero in your homework, or in general, ImageNet outputs, the sort of label with the highest score, instead of one label for the entire image, I want a label for every pixel of the image, which is different from, by the way, instance segmentation. So look at the image on the right. We don't care which one is cow 1 and cow 2. Everything which is painted brown is cows. So that's the difference. But then what we do care is where's the sky, where's the grass, because every pixel will have its own label. So think about how can we use what we have learned so far to attempt this problem. First of all, it's very desirable, right? So it goes without saying that this is a very useful thing for scene understanding for self-driving car. If I can do a semantic segmentation in real time on my sort of camera stream, I instantly know where there are vehicles. I can even do instance segmentation. So I'll differentiate between vehicle 1, vehicle 2, blah, blah, blah. I know where I can drive, which is, say, purple. I know where lane markings are in this yellow, where pedestrians are, where buildings are, so on and so forth. So it's very, very useful. In fact, here's, again, the output of semantic segmentation. It's not detecting everything, but it is detecting, I think, vehicles and pedestrians and buildings in this case. So one idea is the following, and let's see what you think about this idea. I have an image. I want to label every pixel in the image. What I can propose is, let me begin with some window or some patch size. I will overlay that patch onto some part of my image. So I've given you some 3 examples here. And then this becomes my input to a regular object detector. And it just has to produce one output label. So this is just business as usual CNN object classification. Whatever label it produces, I'm going to assign that label to the center pixel of my patch. Okay? So I do all this work to get one label for one pixel when I pass it through the network. And then I have to move the patch around and keep relabeling until I cover the entire image. So it is kind of brute force, right? So it will work, but can someone tell me a reason why we shouldn't use this in practice? Yeah, so it's obviously very computationally inefficient and takes a lot of time. But I would even say that, when you move the patch ever so slightly, let's say with a stride of 1 or 2, the CNN here has learned some features or has broken down this image into some features towards the end of the network. And so when you just move it slightly, you are not using all of that overlapping information. You are treating every patch independently to get one label for the centermost pixel. So not only do you need a lot of instances of this, which is where the computational inefficiency comes from, but you are actually neglecting useful information. So this is a really bad idea, and nobody uses it in practice to do segmentation. But this is, in theory, feasible, right? This is how you would brute force it. So what's a better idea? Okay? Do you have a question? Yeah. Yeah, it is possible. If the animal is green and the grass is green, you would struggle. So it depends upon, can you actually learn not just the color information, but actual features of what the animal looks like. And that's what the CNN is doing. Here's another idea. Okay, let's wrap our heads around this. What you can do is, instead of pixel-wise imaging, you can actually just train a layer of just convolution after convolution. So the purpose of a convolution is to learn these filters automatically. Right? So I can take an input image and just do multiple convolutions. So I will get a big volume of my output. And the way I'm going to train this is, for one forward pass, I will only train on, let's say, the grass channel. On another pass, I will only train on the cow channel. For all possible labels, I'm going to train this fully, it's not a fully connected network, it's just convolutions after convolutions to learn these internal weights. And so at the end, I will have this volume of the same resolution as my input image, because there's no max pooling or any subsampling. And then, since I'm doing this for all my channels, let's say I have C channels, I can simply look at the highest score in the image to produce my pixel. So I know that may not have been clear, so let me break this down into a much simpler example, and then I'll take some questions. So let's say this is my input. My goal is, this is obviously a toy representation of this image, but my goal is that I want to allocate every pixel a class label, where the class labels are these 5 possibilities. Okay, so I want to produce, this is my semantic segmentation output. I want to produce this, basically a map where every pixel has some class label. And the way I would do this is, I treat every class label as its own ground truth, or a different layer mask. And through different convolution layers, I can train them so that the loss for one of the layers was just on the person channel. The loss for another pass was on the purse channel. The loss of another pass was on a different layer. In other words, this picture might help you figure it out. In one forward pass, let's say I want to predict the second channel of my segmentation layers. And this is the output filtered image that is produced at the end of all those convolutions. But the ground truth is just this mask. So I can calculate a pixel-wise loss in this case and do backprop on that convolution. Is this intuition clear on what we are trying to do? So if you do this for all the possible layers of the segmentation map, you can train a fully convoluted network to produce this output. And so what I meant earlier was that, let me actually go back. So let's say at the end of your training, you get some predictions for a single image, you will get some prediction. Let's look at this topmost pixel. You will get some prediction of this pixel for the person class. You will get some prediction for the purse class, some prediction for the grass, some for sidewalk, some for building. So you're actually generating what you can call an entire vector of predictions for every pixel through these convolutions. And so what you can simply do is, if you are normalizing it and passing it through softmax, you can simply allocate that pixel the class which has the highest value of the score. So this is what I meant by saying that you can just do convolutions after convolutions so that you don't perturb the input image size. We want to have the same image size because we want to generate a score for every pixel. And then we just read out the maximum score and allocate that class. So this image is actually like a stacked image of different layers. So questions on this idea of segmentation? Is it clear what we are trying to do and how we do it? So you're still doing, it is clever because you are still doing label predictions. But again, the problem is it is very computationally intensive. You have to train these different layers. By not doing max pooling, you are preserving the same resolution throughout the network. So your filters and your feature maps are going to stack up, and there's no way to reduce them. Yeah.
If we go back to that thing with 5 layers, yeah. So is that possible? Since we have taken care of each of the feature label separately.
Correct.
If that's also we have at a specific pixel, we have maybe like one at person and one at sidewalk.
I lost you, so say that again.
So they have the same size, right, for each of the layer, at each specific like coordination. Are we able to have like just 1 or 0? Is that possible? Like 1 at the person, and also the same value of 1 at the person?
No, the ground truth, the ground truth will come from someone who has painted over the actual image. So you won't have two possible labels for a single pixel.
So there's no issues that overlap.
Yeah, yeah. Any other questions? So this is the, again, intuition. We can obviously spend more time to break this down, but I want to tell you how semantic segmentation really works. We haven't yet actually solved it, because this still has a problem that we are always dealing in the original image resolution, right? So if we have this 250 by 250 pixels, that's a lot of weights. That's a lot of forward and backward passes and a lot of back propagations for different channels as well. So finally, what we can do is the following. We still want to have the property where the output image or the filter map has the same resolution as my input, but I don't want to just do convolutions because it's computationally prohibitive. So instead what I do is I first just train a regular CNN. You have regular conv pool layers to subsample and reduce this image space. So we are learning the features of this map. And at the end, when we have this low-level representation of our original image, we do another operation that we haven't learned so far called upsampling instead of downsampling, where we want to generate the original resolution as our input image. Okay, so we know at least how this downsampling works, right? So it's just pooling and strides and convolution. It will reduce your input from this image resolution space to something which is much more easy to manage and of low resolution, but still preserves the patterns of the original image. What we don't know is that what the heck is this upsampling now, okay? So that's the final piece that I'll explain what is upsampling, and then all of this is going to make sense why we are doing it. Okay, so here's one idea called unpooling. Unpooling is the opposite of like max pooling or pooling in general, where you have an input which is low dimension and you want to generate an output which is of a higher dimension. So some ideas are the following. So this idea is called nearest neighbors, where what I'm doing is for every pixel, I'm unpooling it by a factor of 2. So I am just creating 4 pixels with the same value. Okay, so all these nearest neighbors have the same value as the input. It's naive, but it is one way to increase the resolution. Another way could be what is called bed of nails, where you take the input value and you buffer everything else with 0 and just preserve the input value in one of the locations in your unpooled image size. Okay, now, so in this case, I'm looking at the input and it's always registered at the top left corner of this sort of 2x2 unpooling. So these seem like heuristics, right? And they kind of are. And it's completely reasonable to ask or feel, well, this seems very arbitrary. Why did you choose top left? Why not top right or whatever? By the way, this is called bed of nails because most of the pixels are 0 or sparse, and then you just have some spikes or nails. That's loosely where the term came from. So can we do something better and smarter? Here's another idea. During max pooling, remember, so this is what max pooling looked like if you have forgotten. You had, let's say, a 2x2 pooling window. You simply look at the maximum value, which is 5, and you register that as the output. So we went from a 4x4 to a 2x2. What you do is in this segmentation architecture, for every pooling layer in your input, you have an unpooling layer as well, a symmetric sort of unpooling layer. And instead of doing bed of nails or nearest neighbors, one idea is I look at the input. So let's say we are at this small scale and we want to go to the large scale, so 2x2 to 4x4. I will look at this input and I'm going to keep track of which location was the maximum value at when the corresponding max pooling layer was activated. Okay, so when the image was being downsampled, we keep track of that 5 was present in this bottom right location in the top quadrant. And when the symmetric unpooling occurs, I want to allocate the pixel value to that same location. Okay, so if you look at where the maximum values were on the input, we want to just keep track of where those values occurred in the symmetric pooling layer, and that's the location we will use to input our pixel values. That's another idea. So this is what is called in-network upsampling. So you're simply keeping like a library of locations of where the maximum occurred. And this is the unpooling process. So any questions about unpooling? So far, unpooling is just a function. Okay? We make a choice, nearest neighbor, bed of nails, this fancy stuff, but we are not learning anything when we are upscaling so far. So this is just a fixed choice. So the learning actually occurs with something called transpose convolution. Some people call it deconvolution, which is not the correct term. I think transpose convolution conveys the fact. So let me quickly explain what transpose convolution is. So let's say you have an input 4x4, and we have a 3x3 filter with stride 1, pad 1, and so the output will never change. So by the way, I hope if you haven't noticed this already, the output size is your image minus filter size divided by stride plus 1. So when you use a pad 1, you are automatically increasing the image size by 2 because you have a pad 1 on either sides. If you use a filter of size 3, you will have n plus 2 minus 3. If you use a stride of 1, it gets divided by 1, and then you add 1. So all of this will get cancelled, and you will always be left with the same output size as your inputs, right? So I hope you sort of figured it out on your own during the assignment. So that's why it's very typical to use 3x3, stride 1, pad 1. Thanks to VGG16, that's how we discovered it. But to recap, what was convolution? It was this idea that you have to do this filtering over all possible values. So this dot product, and here's actually a animation which shows how this can be done in RGB space. By the way, it's another quick detour. Once you have these filters, one idea is to just sum them up into a single filter as well. Okay, if you haven't. So some of the architectures do this as well. So you can, you can prevent your network from having too many stacks at each of the layers by summing it up. And also, when you sum it up, you can also add a bias term. Okay, this was a quick hyperlink since we revisited convolution. So convolution was this idea that we will slide this filter over our image and take this element-wise product or dot product, and we'll get the output filter. But notice that if we change the stride of the convolution, we will also automatically subsample, right? We have seen this before, that in this case, with the stride 2, we are not going to be able to cover all the pixels in the same manner, and we are dividing by 2 in the denominator. So since we are skipping some pixels, the output dimension is also reduced, right? So this is just a recap of regular convolution, nothing new here. The transpose convolution is the following idea. Let me explain it, and then I'll show you another example. You want to go from a 2x2 image to a 4x4. One way is to use a fixed mapping called unpooling, and you will use unpooling in the same order where you used pooling during the downsampling. But what do you use in lieu of convolution in the downsampling? What you use is transpose convolution. The idea is I will still have a filter which will have its own weights. I will read the input value of my input image, which is low resolution, and I will simply multiply the weights of my filter with that value. Okay, so let's say the input value was this red pixel. I will have a 3x3 convolution filter. and it will have its own values of the pixels. I'm just going to multiply all of those values with the input and log it as an output. Because I have pad 1, I'm also logging some things that I don't really care about. Then I move over. I will multiply everything with the value in the blue space and log those here. And there would be some pixels where there's an overlap. In that case, we just simply sum the new value with the previous value. The trick is that the weights of these filters are learnable, just like regular convolution. So let me give you another example to make it clear. Actually, a 1D example will make it very obvious. So let's say this is a very simple image. It's not symmetric, and this is my filter. So what I'm doing is, for the first part, I'm going to multiply this input with my entire filter and store that as the output. For the second part, I'm going to multiply the same filter with another value and store that as the output. And there's a part where they overlap, I will sum them up. So what is learnable in this entire picture? It's the XYZ, which can be tuned using backprop. So not only are we learning filters that learn features from our original high-resolution image to the low-level representation, during upsampling as well, we can learn filters like XYZ that do some upsampling, which leads to the best minimum loss at the output. So let me pause for questions, because this is new. Is it clear on what? This is still convolution. It's not just element-wise product. That's the difference. Right? We are not taking an element-wise dot product. We are just scaling the filter with the value of the input, in the hope that during backpropagation, the value of the filters themselves will adjust accordingly. Yeah. So finally, there's another picture which hopefully makes it clear. I'm going to kind of just explain it once. You have your input image, let's say 4x4. It doesn't matter what the actual values are. Actually, the block diagram matters more. And you have your convolution filter. So your filter is 3x3. Your input is 4x4. Here, actually, we don't have any zero padding. So you can already visualize that there's only 4 opportunities for you to slide the filter over. That's why the output would be 2x2. So if you look at this convolution, these are the 4 possible operations. So if we look at this filter, the top row of the filter first gets multiplied by the top row of my image, and I don't care about this 4th value. Then the second row gets multiplied by the first 3 elements of the second row. I don't care about this. Same for the 3rd row. And then I don't care about the 4th row. So here's another way of looking at convolution. This operation, which is 4 distinct parts, I can actually represent in a single shot, in one single calculation, in the following manner. I'll take my filter and I expand it into a large matrix such that every row, look at how many elements are in this row. There are 16 elements from 0 to 15, which is the same number of elements as in the original 4x4 image. So all this is saying is every row of this matrix gets multiplied by my entire flat image to give me the output feature directly. So let me convince you of why that is happening. So let's look at this top row. The top row says this first row of the filter, 1 for 1, and then 0. So why does it say 0? Because 1 for 1 only gets multiplied by the first 3 elements and not with the 4th element. So the next part of my top row of the matrix would be this part of the filter multiplied, this part of the filter followed by 0, because I want to ignore the 4th value again. So just look at the top row. It says 1 for 1, 0, then the second row followed by 0, then the 3rd row followed by 0, and then 4 zeros. So if I take this top row and multiply it by my image, so this is, by the way, a 4 by 16 matrix, and my image has 16 pixels, so I can interpret that as just a 16 by 1 vector. So I have 4 by 16 multiplied by 16 by 1. My output would be 4 by 1. So this row, when multiplied by this vector, will give me this value. So instead of doing this striding and everything, I can just build this convolution matrix once, and then this becomes a matrix multiplication. Okay, so this is what convolution is really. Convolution is a big convolution matrix, which is derived based on the filters and the padding and whatnot, multiplied by the image. You get an output, which is 4 by 1, but we can reshape it into 2 by 2. So what is transpose convolution? It's going backwards. So if someone gives me these weights of the transpose convolution, I can multiply that by my small image. So these weights are now 16 by 4. I multiply that by 4 by 1 image to get a 16 by 1 flat image that I can reshape into 4 by 4. So eventually I have gone from 2 by 2 to 4 by 4. And the question is, which oracle is giving you these weights? It's through backpropagation. So this is another way to look at this transpose convolution layer. So let's go back to where we started, right? So the goal was we want to generate scores at the final layer for every pixel. The problem was if every layer is convolution, it's very expensive. So let's use subsampling to just extract important features, but we do care about the original resolution, so we upsample to the original resolution. And not only are you learning the filters of the downsampling, you're also learning the filters of the upsampling convolution layers. And at the end, you do the same thing. You take the maximum score of all the segmentation layers. Okay, so all of that to just tell you the intuition for, it's still all CNNs, by the way. Nothing really new has happened. Yes, we have introduced this transpose convolution, which is very similar to regular convolution in matrix space. But other than that, we haven't really done anything, drastically different so far. And this machinery is enough to do semantic segmentation. So questions on this, concerns, whether this is going to work or not? So the output here is, indeed, for every pixel, we will generate a prediction for what class that pixel belongs to. Okay, so very quickly, how do we solve this problem? It's actually more straightforward than you would expect. The idea is, not only do you want to detect what object is in the image, which we already know how to do, it's a regular CNN, you also want to draw a bounding box. So if you had labeled data of bounding boxes, and what does a label of a bounding box looks like? It looks like this. You give me the XY coordinates of the top left pixel of where the bounding box starts. So that's 2 parameters I have to predict. And you give me the width and the height of the box. That's all I need to generate a rectangle. 1 coordinate and the width and the height equals a rectangle. So I can describe this box with 4 parameters. So what you do is, you do the regular AlexNet or CNN layer, and you have the fully connected layer, which will give you the prediction of what object it is. But then you have a clone of this fully connected layer, a separate one, which is often called a different head of the network. And this head is just like a regression. So the job of this head is to predict these 4 parameters for that image. And it's trained on examples of images where these 4 parameters were also present. So with the same actual network, you are accomplishing 2 tasks. You are predicting both the object type and you are estimating its location. Right, so you have a regular softmax loss, and then you have just your prediction minus the ground truth loss over here. And you can backpropagate on the combination of this loss. Okay, so it's actually more straightforward. And one thing I want to cover in the next lecture is how you don't have to retrain the entire network every time. You can exploit already existing networks. So let's jump ship back to where I started this lecture, and let me close the loop on this lecture itself. So going back to lane detection, here's a data set of what ground truth may look like. So this is a data set called Too Simple. It's not too simple to actually solve this problem, so the name is ironic. It has thousands of images of 20 FPS, frames per second, split into, I think, 0.7 fraction of training and testing. The type of annotations here is the polylane. So it's not the sort of the image mask. There's just like ImageNet competition, there's two-lane lane detection competitions as well. And one of the networks that did really well and started this field is what is called LaneNet. Now we have other networks which are slightly outperforming LaneNet. So these are some examples of the input image and the ground truth. So even though the ground truth is polynomial lines, you can easily generate a mask for the input image. So now this becomes a segmentation problem. I have a bunch of these images. Each of them has a mask as the output, and I want to learn a CNN with the downsampling, upsampling that produces this as the output. Okay, here's a slightly different image, different mask. There are different types of labels as well. So Too Simple uses this kind of labels. There are other data sets which actually also capture the width of the lanes, if that's what you care about. It's a minor detail, but there's data sets out there that will do that for you. So you have a test image from Too Simple. You can produce sort of your output of where you think the lanes are on that image. So you're producing this mask or segmented image. Why is this a bitmap image? Because you only have one class, lanes or no lanes. In fact, I haven't told you how, but you can also do instance segmentation where you can differentiate between which lanes are, they're all lanes, but you can order them from left to right. So it also does pretty well. Actually, it does better than the non-deep learning stuff that I showed you before, both on straights and curves. So that's promising. The burden here is not on the features and everything. That's easy, right? The burden is labeling that data to train this network, right? That's where all the cost has gone. So at the end of the day, what you are doing is you have a network which is taking the input image, and either it is producing a mask or it is producing these waypoints or polynomials as the regression outputs, right? So in the previous case, we produced an image mask as the output. You can also train a CNN such that it produces waypoints or coordinates for the lane markings, right? So you can, again, you have the ground truth and you have your prediction. You can train the entire network on some Euclidean loss between these two. So the final thing I will touch today is when it comes to predicting lanes or bounding boxes, which is no different than predicting these lanes because you are just predicting these 4 regression parameters. One very good question is, well, what is a good prediction here? Right, so the green is the ground truth, and the red is your prediction. And so, would you say this is a good prediction, or do we really need like exact bounding boxes? It's a very good question. So maybe your response is, well, I only care about figuring out if it is a stop sign or not. I don't really care about where in space is a stop sign. I'm not really flying a drone here. I'm just driving, okay? And I would say, yeah, that's perfect. But then what about this? Okay, here is something you care about a lot. The green is the ground truth of where the car is. So on the top left, you are neglecting the front of a car. Here you are neglecting the rear of this truck. Here you are over approximating so that you don't make an error. And then this looks pretty good. So the question arises is, how do we even evaluate these sort of outputs of localization or segmentation? What is a good prediction? Because we will never get the exact mask or the exact bounding box. And so one popular idea is what is called intersection over union. So let's say one of these boxes was the ground truth and one was your prediction. You compute the area of the overlap between these two, and you divide it by the total area. So the higher the total area, the smaller your IOU, and the higher the overlap, the higher your IOU. Right? So for IOU 0.5, it may look something like this, and for 0.9, it's already like on visual inspection looking like it's a very good metric. So you can train on this as the loss. What is the IOU, intersection over union? In fact, I don't want to spend too much time here, but this is what is happening for the lane detection problem too. Your blue is the true lane, and the red is the prediction, and the green is the intersection of that. So you can use IOU for the part where you are generating a segmentation map as the output. In the other case, when you're generating waypoints, you can use Euclidean loss between the distances of these waypoints. So either one works well. So yeah, we can obviously do this on many, many images. You can compare it to other networks as well. So LaneNet does very well. One problem with LaneNet is that you are treating every lane or every image as its separate instance. There is no notion of hysteresis, or there is no time aspect. You can actually exploit the fact that from one image to the other, especially at 60 frames per second, the lane marking is not going to bend abruptly. It's going to have to be consistent with the previous prediction. So every image shouldn't be treated independently to predict its own lane markings. We should use some history or auto-regression or some lag from the previous predictions to inform our next prediction. And so that's the idea with this modified LaneNet. This is from NVIDIA. So on the left, you will see the raw LaneNet predictions, which are accurate but jittery, or at least not high resolution. And on the right, you will see an output which uses this idea of using history or previous frames to inform the prediction of the next frame. So you can see the right-hand side, the prediction is very accurate, even in the presence of shadows on the lane markings. The prediction on the right-hand side, which uses historical information, is much, much more accurate. So you see we have a lot of significant shadows. LaneNet is sort of struggling. It actually overlaps the lanes with some cars. This is a case of an extreme bend. And look, LaneNet is struggling at the horizon, but this history is again very accurate for an extreme right-hand turn. This is in low visibility. The right-hand network is just modified LaneNet with some temporal aspects. So this is pretty remarkable, right, that you can do that. Under very low visibility, foggy conditions, the prediction is very accurate for a long horizon or a long distance as well. This is at night with some glare and some water on the lens as well, and some reflections from the road, and still we are able to predict with a very high accuracy. Okay, so I will stop here because I don't want to jump into the last topic of this module. In the next lecture, I will wrap up this discussion of how we can train our own network to do lane detection. And then I will also want to cover some other topics about data-driven and deep learning for autonomous driving. So I'll just present you an assortment of all different sort of networks that people have tried and are interesting. And then we will wrap up the course. And I can't believe it's already 3 months. Maybe you feel it, but I don't. So I will see you on Thursday.